Um, Chapter 19 Physics, Theory Video 6, First Law of Thermodynamics. You should be familiar with the conservation of energy idea. So, energy is neither destroyed nor created, right? So, that means it cannot simply disappear or come out of nothing or nowhere, right? So, there has to be a conversion of energy from one form to the other. So, now if all the energy that we put into a gas by heating it uh, should and also by doing work, if you provide energy, so it has to be there inside that gas, right? It cannot go, simply vanish. So that means it will increase the internal energy of the gas, right? So this is written as an equation. Increase in internal energy is equal to energy supplied by heating and work done on the system, right? So delta U, there is a total increase in energy, internal energy, is equal to Q plus capital W. Delta U is the increase in internal energy, Q is the energy supplied to the system by heating, and W is the work done on the system. This relationship is known as the first law of thermodynamics, right? And it is said to be the formal statement of principle of conservation of energy, right? Not only to a mass of gas, for everything, for all situations, it will apply. Energy is conserved. Uh, Energy is conserved, and this conservation of energy is not something that actually was developed overnight, even though now it makes total sense to us because of all the previous knowledge that we have gained for thousands of years. Great thinkers, great scientists went through a lot to figure out that this was true. So just like that, there are many other theories that you might one day will discover. The sign convention that is used in the first law is very important. A positive value of delta U means that the internal energy is increasing. A positive value of Q means that heat is added to the system. And a positive value of W means that work is done on the system. So negative is the opposite of that. Negative on delta U means the internal energy has decreased, that is, heat is taken away from the system or work is done by the system on the surrounding, right? So there is an expansion, right? So like we discussed earlier. Uh, Imagine a gas heated from the outside in a sealed container of a constant volume. So here we are not talking about any work being done because it has a constant volume. So W is 0, and the first law equation will ultimately become delta U is equal to Q, right? So all the heat that is being added will become internal energy of the gas, right? If the container was able to expand a little, right, as the heat is added, then we have to be very careful. Now if you compress a gas, then it is work on done on the system. W is positive. So if it expands, you have to be very cautious because the gas is doing work on the surrounding. Right? So the by the gas on the surrounding work is done, therefore W will have to be negative, right? So then the W is going to affect the delta U, right? So it would be then delta U is going to be, total internal energy is going to be slightly less than what it would have been if it did not expand, right? I hope you understood. If you did not, please tell me. Then a gas doing work. Gases exert pressure on the walls of their container. You know that, right? When a gas expands, the walls are pushed outwards. So you can take a syringe and think about this. If you close, please remove the needle, don't hurt yourself. Remove the needle, and then the open end of the tiny hole, you close it with your thumb and try to push from the syringe hold, and then you can see that it is getting compressed, and then when you release it, you will see the compressed gas will do some work by pushing the syringe outwards. So that is work being done. uh, in a steam engine, expanding steam pushes a piston to turn the engine. And in a car engine, the exploding mixture of fuel and air does the same thing. So that is an important situation. That is, work is being done by the explosion of gas. So in an internal combustion engine, what happens is oxygen and fuel is mixed together to produce gases. These gases will move the pistons, and the pistons will ultimately rotate the wheels. So this figure shows a gas at pressure P inside the cylinder of cross-sectional area A. The cylinder is closed by a movable piston. Then the gas pushes the piston a distance of S. So this distance, it is being pushed. If we know the force F exerted by the gas, then we can deduce an expression for the amount of work done by the gas, right? Because we know the equation of pressure. Pressure equals force upon area, force over area. Then force is equal to pressure into area. Then we have another equation. Work done is force into displacement, right? Work done is force into displacement. Then we can get, we replace force with pressure into area here. Then work done is equal to pressure into area into a displacement. But the quantity A into S is the increase in volume of the gas, right? So the area into this length, so that volume, right? That particular volume, that is the shaded volume in figure 19.10. So this area is what we are talking about. Okay. We call this delta V, that is the change in the volume, where delta indicates that it is a change in V. Hence the work done by the gas is W is equal to P delta V, that is pressure multiplied by the change in volume. You need to if you can try to memorize this, how we derived at this equation, because that might be important. So the main equation, this is something that you must remember, W is equal to P delta V, right? Work done when the volume of gas changes at constant pressure. So obviously this is going to be relatable to only to gases, and it has to happen under constant pressure. So the work done would be W is equal to pressure into delta V. So in here we are assuming that the pressure does not change as the gas expands, right? So this is actually ideal gas principle, and extension of that as well. This will be true if the gas is expanding against the pressure of the atmosphere, which changes only very slowly. Now we are going to figure out how does the first law of thermodynamics apply if you can compress a gas. This can be done in different ways, but we can consider two limiting ways, right? So now, first of all, you have to, now you should be able to you should have in your memory the first law of thermodynamics. So the first law of thermodynamics suggests delta U is equal to Q plus W, right? The internal energy is equal to energy supplied by heating plus the work done on the system. And please remember those sign signs, how the signs would affect. Now, uh, when you compress a gas, the how does it apply uh, apply in practice? Now, not allowing heat to enter or leave the system is something that we must do. So now, in when you explain how this is going to be in your practical paper, when you have to explain, you have to give these details, right? Not allowing heat to enter or leave the system. This can be done by pushing the piston into the syringe very fast or by insulating the syringe. So it has to be done very quickly. So then it would not, it would not have enough time to waste that much of energy. In this case, Q is 0 and delta U equals W, right? So the work is being done. All the work done by pushing in the piston increases the internal energy of the molecules. In this case, the kinetic energy of the molecules increases and the temperature increases unless there is a change of state, right? So, uh, what happens is basically, now when you do the work, right, will that work the we push the piston in, and that increases the internal energy of the molecules, right? So when the internal energy is increased, so that affects the kinetic energy of the molecules and the temperature would rise. If there is a change of state, then the temperature rise uh, would not happen. You know why? Because there is latent heat. Then at constant temperature, then what are the two what are the what are the constant temperature effects? Now you push the piston very slowly, right? So it is done so slowly that the temperature doesn't change. So it has to change, it has to remain at constant room temperature. So this is known as isothermal change. The kinetic energy of the molecules will remain constant, right? You might have problems here because we learned earlier that when the volume is reduced, the kinetic energy increases, right? But here it is done so slowly that it remains constant. The molecules become slightly closer together, and this may mean that their internal energy becomes slightly less. But the change is very small, right? If U is constant, then delta U is 0, and Q plus W is going to be 0. This means if you do positive work W, then Q has to be negative. So the heat is lost from the energy syringe, right? You do positive work on the system, and the system will lose energy. So that means when you are pushing it together, right, the kinetic energy increases. The kinetic energy increases, but because they are coming closer together, right, then it will have a negative electrical potential energy, and as a result it is going to be 0. I hope you understood. The system will lose the heat to surrounding by conduction or some radiation something, and if you put out the piston out slowly, the opposite will happen. W is negative and Q is positive, and heat will enter the system, right? I hope you understood that, right? Let's write down the note. First law of thermodynamics. By extension of the law of conservation of energy, all energy that is supplied, all energy that is supplied to a system should increase its internal energy. And please write down this equation. Increase in internal energy equals energy supplied by heating plus work done on the system. Increase in internal energy equals energy supplied by heating plus work done on the system. And then write down delta U equals Q plus W. Leave a line and write. This is the first law of thermodynamics. And underneath that, write down delta U equals increase in internal energy, Q is the energy supplied to the system, W is the work done on the system. Leave a line and write. Sign convention is important in this law. A positive delta U means internal energy is increased. Positive Q means system is heated, and a positive W means work is done on the system. Negative sign would mean the opposite. Leave a line and write. When a gas does work, the pressure results in a force being applied on a particular area. Through that, we can develop an important equation. Leave a line and write. Pressure equals force over area. Then from that, F equals P into A. Because work done is equal to force into displacement, we can get the equation W equals P into A into S. Right? Right? Then pause the video and draw this. If not, you would find it difficult to understand. Then write down, because A into S is increase in the volume of gas, W equals P delta V. Work done when the volume of a gas changes at constant pressure is what is obtained through this equation. Below two limiting ways will explain how first law of thermodynamics apply. Number one, not allowing heat to enter or leave the system. By pushing the piston into the syringe very fast, or by insulating the syringe, we can limit Q to be 0. As a result, delta U would be equal to W. And this will increase the internal energy of the molecules and the kinetic energy increases and temperature increases. Number two, at constant temperature, the syringe is pushed in so slowly temperature stays constant. So if the temperature remains constant, kinetic energy remains constant. That also write down. Kinetic energy remains constant. But because molecules are slightly closer, internal energy U becomes slightly less. So that means when we push the piston to do positive work W, then Q is negative. But because they balance out, internal energy does not change. I hope you understood. If you have any questions, please ask them. After you have gone through this, please do question number 3 and 4. I will discuss these questions at the end of the lesson.